All right, so in today's lab, you're gonna have a setup something like this. Now there's other labs that where it's going to make a bigger difference in, we'll have potentially so much weight on this that this thing might start to move or tip over. This one is not as crucial. Not yet. How many of you have used the LabQuest before? 1, 2, 2.5. I forgot. Use this one. Actually, I might be able to make this work. Is there another one of these rods lying around here? That one's a part of that piece of equipment, so I don't want to dismantle with it. I'm just gonna go grab another one. Even though I could make this work, it's not realistic that, since the lab doesn't call for doing it that way. I'm just gonna let the camera run and I'll be right back. All right, so we're going to hang these force sensors on these, and the force sensors have a place to thread this in. And the bigger bars here will fit. There we go. And I'm hoping I grab 2 force sensors that are still good. All the equipment that we have is the one most likely to go awry. All right, and then these will plug into a LabQuest. Now this is a LabQuest 3. The lab says LabQuest 2. Matter of fact, we can start handing those out. It doesn't matter if you use a 3 or a 2. It is, well, you basically take it down the next title, so it's, yeah, 3 pages. Just give you the 3, so. All right, so this is going to be the basic setup right here. We're going to hang this from these force sensors. Now, one of the things that you'll be doing in this is trying to figure out where the center of mass is of the meter stick. It most likely is going to be somewhere around 50 centimeters, but since this is for measuring length, having this perfectly balanced in the middle, probably not the way it actually is. So ideal and reality mix. So the fulcrum holder, the fulcrum. And when I put it in there, I'm either going to put it in like this or I'm going to put it in like that. I recommend doing it this way. If you do it that way, that's the path to madness, because this is incredibly persnickety when trying to balance it this way. Clearly not balanced. So I'm going to shift it over. I need to shift it over towards the lower side. That's slightly better, it's still not perfect. Still a little bit off. Cheated over 1 more millimeter. And sure there are extra copies at this point. And you got one. Now, in the lab, I specified, record the position plus or minus 0.1 centimeters, in other words, to the nearest millimeter. So the small marks on here are millimeters. And so that is at 49.7 millimeters. So you would write down 47.9 centimeters. So you write down 49.7 in this plane. That's not what you're writing right now. This is just an example. You will have your own meter stick. The mass of the meter stick. Well, this is used for finding the center. So the mass of the meter stick does not have this. And so you pull out the triple beam balance. Now most of the meter sticks are somewhere around 100 grams. There are some exceptions, but if you end up with something like 200 grams, then probably there's a mistake somewhere. When using the triple beam balance, please make sure that this is in the groove. There are grooves along here that a light touch is not going to shift it. I have seen some people put it sort of halfway in between so that a light touch will shift it. It's not secured, so please make sure it is in a secure spot. This is a balance, and therefore, since it is a balance, it measures mass. Scales measure force, balances measure mass. This one's more massive, or this thing's broken. Wow, this one's more massive than usual. So it's 160 something. And for the mass, it tells on here to the nearest 0.1 grams, which is basically the scale on this one. So it's 162.6 grams. And again, this is for this particular meter stick. Now, it's expressed here in kilograms, but I measured in grams, so I need to convert it to kilograms. Grams to kilograms, 3 decimal places. So 0.1626 kilograms. Now, kilograms is in parentheses, so you'll just write the number. At this point in class, I assume you're in chapter 2. What have you finished chapter 2? What have you done in chapter 2?
Just like motion. Talk about like motion and like acceleration and velocity.
You're doing motion right now?
Yes.
Not doing forces?
I read about forces.
Yeah.
Chapter 2 is forces, chapter 3 is motion. So you're doing 2 and 3? Okay. Do you know the
Are you talking
formula?
about the online class?
Yes.
I don't know, I'm really confused about that.
He gave us
class, too. It's not
chapters 2
really-
and 3.
Like
2 and
2
3.
and 3
To kind of start on.
combined.
That's what he has. That's
Okay.
at least what I started on.
See, from a physics point of view, I would love to teach chapters 2 and 3 simultaneously. So that's because those 2 chapters sort of set up the foundation for the rest of the course. And most textbooks will do motion first and then forces. Hewitt does forces and then motion. There are advantages to both. All right, so the formula for weight. In unison would be really cool right now. Do you know what Newton's second law is yet?
Yeah, it's Wait, I have to remember.
An object that is in motion.
That's first one. That's
Yep,
the
that's
first.
first.
Did I miss the second?
Second law is.
It's the formula one.
Oh,
The third one is for every force, there's an equal and opposite force.
yeah.
Alright, so Newton's second law, which I consider the most important equation in all of physics, is that the total force acting on an object, so this is, generally in physics you just write F, but it actually represents the total force or net force, is equal to mass times acceleration. Newton's second law. Now, he wrote it slightly differently. Well, one, he wrote it in Latin, but. So sometimes you'll see it written this way, but this is what I prefer. So if I take an object and I just drop it, what are all the forces acting on it as it falls?
Gravity.
Direction and magnitude.
All right, so first off, and this is potentially a me thing, but gravity is a very huge topic, of which the force from gravity is just a small aspect of it. So either force due to gravity or weight. So the weight. Somebody else said some other forces.
Direction and magnitude.
It is a vector, so it does have a direction and magnitude. What's the direction of the weight acting on the object as it falls?
Downward.
Okay. So if the force is downwards, what's the direction of the acceleration?
Downward.
It better be, because I have only two vectors here, so they better be in the same direction. So let's make down positive, because I can make any way I want positive. So I have any other forces? There is one other force that acts on an object as it falls. If you've ever done, why am I blanking on this? Skydiving. Yeah, okay, or generally air resistance. So we are ignoring that very nicely, because it gets way complicated if you want to bring air resistance into it. So if we ignore air resistance, the only force acting on the object as it falls is its weight. And that's going to be equal mass times, well, since the only force is the force due to gravity, the acceleration is the acceleration due to gravity. Symbolized by what letter?
G.
Lowercase g, more specifically. Now the lowercase g varies depending upon where you are. The world average is 9.805, 806, somewhere around there. On the moon, it's about 1.6, 1.7. On Mars, I think it's 2.7 or 3.2, one of those two numbers. For Winston-Salem, .798. At this point, they pretty much mapped the entire world, although you do have to do some interpolation. But it turns out that one of the early devices they used for measuring the acceleration due to gravity here was done right out there on Silas Creek, basically level with us, in the median where you got the traffic light. It's where the next road tees into it. That's the median. The device was there. So we have a pretty good measurement of acceleration due to gravity here. So on labs, if you see under notes, use 9.798 meters per second squared, that's because we're talking about here in Winston-Salem. On a lab, never ever use 9.81. That's the rounded off for the world average. That is not here. All right, so we have a formula here for weight. It's just the mass of the object as measured by the triple beam balance times the acceleration due to gravity. And if you'll notice up in notes, I do in fact say, for this lab, use G equals 9.798 meters per second squared. So what is the weight of the meter stick? Well, if someone has a calculator, you'd be kind enough.
Approximately 979.8 if you use.
Sorry?
So if you use the average of 100, or it was, we had 160.
Oh, use this value for the mass. 0.1626 kilograms times 9.78, oops, sorry, 798 meters per second squared.
1.59.
1.59?
And then 31,548.
Not all of it significant, but units?
And Newton.
I think somebody just said it.
Newton.
Yep. All right, so I know where the center of mass is of this, I know what the weight is of this, and now let's find out if physics works. But it is a physics demonstration, so what are the odds that it actually will work? Lab quest, I pulled out over here. Now the LabQuest 2s are slightly different, but if you will notice, if you're using either LabQuest, there's 3 ports here and there's 2 ports here. Some of the sensors use these, some of the sensors use these. And this one happens to use the ones on top. So, nope. Nope, they use these, the ones on the end. If you're using a LabQuest 2, these are hidden by a flap. Now, these things generally don't hold a charge particularly well. So it's possible that you'll need to plug it in. And there are loads of plugs in the other room which we'll be using. Also, there should be a stylus, which I'm not seeing attached here. Don't touch the screen with a sharp instrument like a mechanical pencil or pen. It's starting, please wait. All right. All right, so now it's acknowledging I have my 2 sensors, and I'm assuming all of you have great eyesight. Or if you have bad eyesight, you're sitting somewhere near the front. All right, so first thing I need to do, there's nothing on them other than these strings, and I really don't want to include those. So I've got them hanging on there, and I'm going to zero it. So I just touch the screen, and I hit 0, and it should go to 0. And so they're both somewhere around 0. Now there's some fluctuation. The room shakes a little bit, and the sensors are a little hypersensitive. I believe I said put this on. Set on plus or minus 50 newtons, and these are set on plus or minus 10 newtons, so I'm going to flip the switch over to 50. And notice this, one of them is already up to 0.33, so I want to zero that again. And it's possible that it's just a bad sensor. So far, so good. And then I put this into here. Now I do specify where this is supposed to sit. So please pay attention to where it's supposed to sit. I want this to be level. Is that level? Which side, how do I
It
up or
needs to
down?
go a little more up this side. That's about good.
All right. So now I have these 2 forces here. For one of the force scales, it's at 0.73. For the other one, 0.89. Those are the forces that are acting up. Is this in equilibrium? Why not?
They're not equal.
No, not the reason why it's not in equilibrium. What does equilibrium mean?
The forces that are approaching it, that are affecting it, and the ones that are equal. So the net force would be 0.
Okay, so net force is 0, so equilibrium. Actually, it's 3 different meanings. In terms of force, total force, that's just, the capital sigma here is just to indicate totals. The total force is 0. Because F equals ma, the total force is mass times acceleration, equilibrium also means acceleration is 0. And since acceleration is related to the change in velocity, it also means the change in velocity equals 0. I'm not saying the velocity is 0, just the change in velocity. So I have, if I look at the forces acting on this meter stick, I have a force acting up of 0.73 newtons, a force acting up here of 0.89 newtons, and a force acting down here of 1.59. We'll just keep it at 1.59 newtons. So experimentally, the forces acting up should equal the forces acting down. Let's find out how close we get. So my total force, if I assume up is positive, let's change that. I have positive 0.73 plus 0.89 minus 1.59. And what do I get? Oh. And that will ultimately end up being newtons. So it's not 0. It should be, but it's not because it's physics and perfect results are rare. So